In this video, we're going to start looking at kinetics. So first thing we're going to talk about is reaction order. So at a constant temperature, the rate or speed of a reaction is proportional to the frequency with which the reacting molecules come together. What that means is the more our two reactant molecules come together, the faster our reaction. And our rate constant, K, is really telling us the speed of our reaction. Now, when we talk about kinetics, we're going to be talking about velocity, which is the speed at which a product appears or a reactant disappears. So for our very simple reaction of A going to P, the speed of this reaction is equal to the change in P over some change in time, which is equal to the change in A over some change in time, or Ka. So remember, K is our rate constant, and A is the amount of stuff we have to begin with, our concentration of A. And what we're showing here is called a first order reaction or a unimolecular reaction. That is based on only one molecule. Your velocity is always in units of molar per second. So if our equation for velocity is K divided by or multiplied by concentration, and concentration is always in molar, K must have a units of per second. Now we can go a little more advanced mechanism, which is 2A goes to P. This is called a second order reaction because we have two things, or a bimolecular. Here, our velocity is equal to our change in A over time, which equals Ka squared. A squared because we have two A's. Here, velocity, again, has units of molar per second. Since this is A squared, K must have units of molar minus 1, seconds minus 1. And this minus 1 just means you're on the denominator of a fraction. Our other bimolecular reaction is if we have two things, instead of two A's, if we have two different things coming together to form P, velocity equals the change in A over time, which is equal to the change of B over time, because they're a 1-to-1 ratio. The rate constant is Kab, and it has the same units. Anything higher than a second order is really rare. So termolecular, three things coming together is rare. Fourth and unknown are higher because for these reactions to happen, all of these things need to crash into each other at the same time. So having four things crash into each other at the same time would be extremely rare, so we don't really see those at all. So let's look at first order reactions. So we're going to be talking about rate equations, and they will help us talk about the instantaneous reaction velocity, or the speed of the reaction at the very start of the reaction. And to plot this, plot a first order reaction, we plot the natural log of A divided by time, which is our equation is the natural log of A equals the natural log of how much A you started with minus K. So let's say that you're measuring a reaction, right? And you start with some amount of A, and you just see over time how's that change. Well, if it's a first order reaction, you can take the natural log of it, and you can find your rate constant because the slope is minus K. You can also do this without having natural logs, and that is the amount of A equals the amount of A initial E raised to the power of minus KT. So with a computer, you could actually use this form and figure out K. Now for first order reactions, and for all reactions, we have something what's called the half-life. The half-life is the time for half of your reactant to initially decompose. So how long does it take for A0 to become 1/2 its starting concentration? And if it's a first order reaction, this time's actually constant. It doesn't matter how much initial reactant you have for a first order reaction, your half-life is always 0.693 divided by your rate constant. So if you have 100 grams of A or 1,000,000, half-life is still the same speed. Now that's different for a second order reaction. So if we had a second order reaction, the way we could plot it is 1 over A on the y-axis and time on the x-axis. And then our slope here will be K, and our y-intercept would be 1 over A initial. Half-life, though, is not constant for second orders. Half-life of a second order reaction is based on how much reactant we have. So the half-life for a second order reaction is 1 over K multiplied by how much A initially you had. Now, let's talk about the kinetics we're mostly going to use for enzymes, and that's called Michaelis-Menten kinetics. So our general enzyme scheme for Michaelis-Menten is that an enzyme plus a substrate will form an enzyme-substrate complex with a rate constant of K1. And this can break down to reform enzyme plus substrate with a reaction order of K minus 1. This enzyme substrate can also go and make product plus enzyme, which is K2, has a rate constant of K2. So our velocity of making product is equal to K2ES, the amount of enzyme substrate we have and whatever this rate constant is. And our change in ES over time equals K1 E times S, so we're making ES, minus K minus 1 ES, we're destroying ES, minus K2 ES. So this should actually say K2, not K minus 2. K2 ES, we're making product and destroying ES. So to do Michaelis-Menten kinetics, to make an equation for enzyme kinetics, we need some assumptions. So our first assumption in Michaelis-Menten is that our second reaction is irreversible. That is, once we make product, we cannot go back. So that's one assumption for Michaelis-Menten. 2, the amount of ES is not going to change. It's going to be at a steady state. So our change in ES over time is actually equal to 0. And that's what this plot is showing, is that after a certain amount of time during the reaction, the amount of enzyme substrate complex will be at equilibrium. That is, it won't change. Our third assumption is that the reverse reaction of ES breaking down to E plus S is much bigger than our K2 reaction making product. That is, we are much more likely to break apart back into enzyme plus substrate than to make product. And those are our first 3 assumptions. Now, along with this Michaelis-Menten, we can also define a new term, which is called Ks, which is the dissociation constant of the first step. And Ks is equal to the reverse rate constant of the first step divided by the rate constant of the first step. So K minus 1 divided by K1. This is equal to amount of enzyme times amount of substrate divided by enzyme substrate complex. Now, we're going to continue with the derivation of Michaelis-Menten here. And when we do a reaction, we need to be able to measure stuff. So in the previous slide, I was talking about enzyme substrate complex and free enzyme, not bound to a substrate. You cannot measure that in a reaction. It's impossible to know. But what you can do is you know how much enzyme you had at the start of the reaction because you made the reaction. You put in that enzyme, so you know the concentration. And the concentration of enzyme total is equal to the enzyme not bound to substrate plus substrate. So it might seem random I'm bringing this up, but we're all going to bring it to a nice equation at the bottom of this page. All right, so going back with our previous statements on the previous page. One, we said we can derive an equation for the change in enzyme substrate complex. And we said that the amount of enzyme substrate complex during the reaction won't change. So the change in enzyme substrate per time is equal to 0. So by setting this equation that I'm underlining here to 0, we can say that K1 ES equals K minus 1 E plus S plus K minus 2 ES. If you ever get lost with this K1, K2 business, make sure you look up here in the top right. This is the equation, the enzymatic equation we're working with. That's where all the variables are coming from. Now remember, we have these terms of enzyme, free enzyme. We don't want that, and we also don't want ES complex as well. So when the first thing we're going to do is when we get this free enzyme, we're going to substitute it with enzyme total divided by ES. And so we can simplify our equation now. We're going to do a lot of rearrangement here, but eventually we can change this equation to say enzyme total minus enzyme substrate complex divided by substrate divided by ES equals K minus 1 plus K2 divided by K1. This is the term we care about, K minus 1, K2 divided by K1. We have a special name for this term. It's called the Michaelis constant. Km equals K minus 1 plus K2 divided by K1. So we're going to be using the Michaelis-Menten constant here. Now, moving on with our derivation, we have this term, and we have a bunch of ES's in there. Remember, we don't really want ES. We can't measure it. So we're going to make an equation that's solved for ES. So we're going to do some algebra here. And we have ES equals enzyme total times substrate divided by our Michaelis constant plus substrate. So we have a term for ES now. And when we're doing kinetics, remember, we want to talk about velocity. That's what we're measuring in the experiment. How fast is this reaction going? How fast is our reaction catalyzed? Or how fast is our enzyme catalyze a reaction? And so when we're doing enzyme kinetics, you usually measure the velocity at the very first start of the reaction. Like within a second, how much product did we make? This is called initial velocity, V0. And that's equal to the change in product divided by the change in temperature, or time at initial time. So like at time 0, how much product did you make? Well, this is equal to our rate constant K2 multiplied by how much enzyme substrate complex we have. We have a term now for enzyme substrate complex, so we're going to replace this term with ES to get our initial velocity equals K2 ETS divided by Km plus S. And we also have another term called Vmax. So Vmax is the fastest you can go. So Vmax is, let's say all your enzyme has substrate in it. So if they're all bound to substrate, they're all making product. So the fastest your reaction can go is based on how much enzyme you have multiplied by the rate constant from going from ES to product. And so your Michaelis-Menten equation, that is the equation for measuring the velocity or the speed of a reaction if your reaction's an enzyme, is equal to K2 ET multiplied by S, so enzyme total multiplied by substrate, divided by our Michaelis constant plus S. And we can actually take this K2 ET and just say initial velocity equals Vmax multiplied by substrate concentration divided by Km plus substrate. Now, let's look at some of the power of Michaelis-Menten kinetics and why we used some of these variables. Alright, so we have this term Km, the Michaelis constant. And Km tells us something important. So if our substrate is equal, the amount of substrate is equal to Km, and Km is just a number, we're going to be at 1/2 our maximum speed, Vmax divided by 2. So when you are plotting kinetics data, if you find your maximum velocity, if you go to 1/2 that maximum velocity, find that speed, go over to your kinetics plot until you hit the curve, then you drop down to substrate concentration. That substrate concentration would be the Michaelis constant, Km. All right, and Km kind of gives you an idea of how fast an enzyme is. How good of binding the enzyme is. So the smaller the Km, the faster or the easier it is to get to Vmax. So that's what Km really means. The smaller the Km, the easier it is for me to go to Vmax. So let's substrate. I really bind my substrate and really want to do catalysis on it. So Vmax is low. Sorry, that's supposed to be if Km is low, then maximum catalytic efficiency is achieved at low substrate concentration. So that's supposed to be Km right there. So Kcat is turnover number. So that's another variable we can talk about for Michaelis-Menten kinetics. Kcat equals our maximum velocity divided by our enzyme total, or how many reactions can we do per active site per time. So how fast we're going divided by how much enzyme we have is Kcat. Well, we can take these two variables, Kcat and Km, and if we divide the two, we get an idea of catalytic efficiency. That is, the bigger the number Kcat divided by Km is, the better or more efficient your enzyme is. And really, your most efficient enzymes are what are called diffusion-controlled limited. So if you have a Kcat divided by Km, that's 10 to the 8th or 10 to the 9th, as we see for some enzymes down here, what that means is your enzyme works so good, the slowest step of your reaction is your substrate actually diffusing to your enzyme. That's diffusion-controlled limited. But yeah, just keep in mind Kcat divided by Km. The bigger the number, the more efficient your enzyme is. Now, how do we actually measure Km and Vmax experimentally? So what you do is that you do a bunch of reactions where you change your substrate concentration and you hold your enzyme constant, and you just measure initial velocity. And one plot you could use to figure out these constants is a double reciprocal or a Lineweaver-Burk plot. So you take your Michaelis-Menten equation and you rearrange it where 1 divided by initial velocity equals Km divided by Vmax multiplied by 1 divided by substrate plus 1 divided by Vmax. This is the Lineweaver-Burk equation. 1 divided by initial velocities on the y, 1 divided by substrates on the x. And when you plot your experimental data on a Lineweaver-Burk, wherever your x-intercept is, that's minus 1 divided by your Michaelis constant. Wherever your y-intercept is, that's 1 divided by your maximum velocity. And your slope is Km divided by Vmax. So with this type of experimental setup for any enzyme, you can find Km and you can find Vmax. And once you find Vmax, you can find Kcat. And if you know Km and Kcat, you can calculate the catalytic efficiency of your enzyme. Now, that was enzyme kinetics. Let's talk about pathways now. So when we're doing steady state kinetics, that is ES is at a steady rate, we actually can't tell how the reaction runs. We can use it to eliminate certain models, but we don't know how it actually works. What I mean by that is, let's say we have enzyme plus substrate, and they go to an enzyme substrate complex. Then they can go to an intermediate. Then they can go to a product and make your product. That's one mechanism. We have a second mechanism where you actually get two different intermediates, EX and EY, that go to your product. You don't know which one's right because you're just seeing product come out. And so the mechanism of enzyme kinetics is really sort of a black box. You know what goes in, you know what goes out. You don't really know how that happens, and really kinetics can't really tell you that. You have to use other experiments. But we're just going to look at some basic mechanisms that could be could be used by your enzyme. And we're going to look at bi-substrate reactions because 60% of all enzyme reactions use two substrates. Michaelis-Menten, we're only talking about one substrate, so here we're talking about two substrates. And so an example is A plus B goes to P plus Q, or here we just have a bond rearrangement, right? And really, you only have a few ways that a bi-substrate reaction could happen. The first is sequential. And the sequential mechanism is that all substrates combine with the enzyme before a reaction can occur. And you have two types. You have an ordered sequential reaction or a random sequential reaction. Ordered is A always goes on first, and then B goes on, and then P goes off, and Q goes off. So it matters the order. Random is it does not matter the order. First A goes on, then B, but it's totally possible that B goes on, then A, and then P could come off, then Q, or Q could come off, then P. So random is it can go either way, coming on and coming off. Ordered is it has to follow an exact order. Now, you can also have what's called a ping-pong bi-substrate reaction. That is, A comes on, then a product comes off, B goes on, and then another product goes off. So ping-pong, ping-pong. And you can determine the sequential versus ping-pong via certain experiments, but not just through kinetics. You will have to do some more advanced experiments to figure out what is actually happening. Experiments that we're not really going to talk about here in the kinetics section. We're just going over basic kinetics. That's it for this very long video. I will see you in the next one.